There you go.
All right, thank you, Michael. So let me begin my talk with an apology because you were supposed to hear a talk by Andrew Melatos, but unfortunately he wasn't able to make it, so you're stuck with me. But Andrew kindly recorded a talk, so we'll make the slides and the recording available, as Michael said, and have a discussion session on Thursday. So if at some point you can take the time to go through the slides and hear what Andrew recorded, then we can discuss on Thursday, and I think what he prepared follows on quite nicely. So I'm just going to give a rather basic overview today of the kind of models that we do to model superfluidity in neutron stars and the kind of problems. Or else. And then Andrew's talk actually contains many more details, so I encourage you to have a look, and then we can discuss on Thursday. Okay, so the title was quite generic. It was quantum turbulence in astrophysics. I'm going to focus on neutron stars. So what we're talking about here is an incredibly compact star. So we're talking about something that has roughly the mass of the sun, but compressed in a 10-kilometer radius. So that means that if you work out the average density, you end up with densities that are higher than nuclear saturation density. And so what you have here essentially is what's left over after a supernova explosion, and the core starts to collapse, but then the collapse is halted essentially by neutron degeneracy pressure. But there's a lot more than that to neutron stars. In fact, you can't model these objects as just a Fermi gas of neutrons. If you try to do that and work out a maximum mass, you'll get something that's below 1 solar mass, while we observe neutron stars of up to 2 solar masses. And actually what plays a role there are the interactions between these neutrons. So the residual strong force here is important. And here these high density cores of these objects is more or less the only place where you can study this, this region of the QCD phase diagram, let's say, because in terrestrial experiments, you're always looking at systems that are at low density and high temperature. While the interior of a neutron star is very high density, but low temperatures. Because if we look at the temperatures in these systems, then we're talking roughly 1 keV, but the Fermi energy at these densities is around 50 MeV. So these are cold systems, and as such, we expect, we expect the neutrons to be superfluid and the protons to be superconducting in the interior. And then there's a lot more we have to consider when we model these systems, because the outer lower density layers will form a crust. So you have nuclei in a lattice, like in a terrestrial crystal, and you have to deal with large magnetic fields, rapid rotation. Of course, this is very compact, so ideally you would like to do all this in general relativity. But this is what we want to focus on today. And if we try to actually look at this a bit more quantitatively, and you look at the pairing gaps in the neutron star, this confirms that mature neutron stars are expected to be superfluid. So in the inner crust, you will have the protons are in clusters, so they're in the crust, they're in this crystal. But the neutrons will have S-wave pairing, which becomes P-wave in the core, and then in the core, the protons also pair. And if we look at typical numbers, we have critical temperatures around 10 to the 9 up to 10 to the 10 Kelvin. Mature neutron stars are going to be, for the standard pulsar population, around 10 to the 8 Kelvin, that's interior temperature or colder. So we expect essentially superfluid throughout. And as we are all well below the transition temperature, we usually take the 0 temperature approximation, although note that there is a density dependence of the gap. So in theory, there are always regions in the star where temperature may be important.
I have a question.
Yeah.
You compare neutrons and protons, but the star must be electrically neutral.
There's electrons. There are electrons in there as well. So it is neutral, of course. So you have neutrons, protons, and electrons. possibly muons. You could have hyperons in the core as well. So the electrons are always normal though. So for this game, I wasn't mentioning them. You are of course right. You need electrons in there because the star has to be electrically neutral. Okay, so if we want to try and understand this system, again, we have to understand it over many different scales. So this is somewhat similar to what Professor Berenguer was showing yesterday. So one has to start from the microscopic scale, so scale of Fermi scale or something like this, where on the one side you need to understand the interactions between subatomic particles that give you the equation of state. But then we have the superfluid. We also need to understand interactions between a vortex, say, and the nuclei in the crust, to which we may pin. But then if we want to do hydrodynamics, we want to move up in scale, we want to deal with fluid elements. So we have to average over several vortices that define superfluid velocity for our fluid element. And this is already quite a jump in scale because you have your vortex that has coherence length of, depend on density, but say 10 Fermi. But then the separation between them is quite large. It depends on the rotation rate of the pulsar, but it can be up to a millimeter or something like this. So this is already a huge jump. And then I want to average over many of them to get my fluid element inside the star. And then I want to do hydrodynamics and get up to the radius of the star, so up to, say, 10-kilometer scale, where I can model the dynamics of the star and then compare to observations.
Excuse me a question. Is there a temperature gradient across the radius?
So, in general, yes. So the strongest temperature gradients are generally in the outer layers. So you can treat this as a kind of heat blanket. And then at that point, the roughest model you can make is isothermal, at least in the core. In practice, though, things like conductivity, etc., are density dependent, so it will not be exactly isothermal. But the strongest gradients are really in the outer region.
It will be counterflow, right?
I'll show you. We'll talk about different kinds of counterflow.
Yeah. What distinguishes in your graph inner crust from outer core? You have this dash.
Okay, so here you have a crust. So what happens here? It's basically a standard kind of crystal like you would expect on Earth.
Yes,
then here, so when you get into here, the neutrons begin to drip out of the nuclei, so it becomes favorable to have a gas of neutrons, which then can be superfluid. And when you get to the core, then you just have a fluid, so you don't have a crust anymore. So you have, at this point, this is basically a fluid of neutrons, protons, and electrons. And then this question mark is that at higher densities.
It's already a fluid on the right?
Well, here you have you still have a crystal, right? So you have the protons and electrons form clusters.
So neutron fluid embedded in a crystal of other stuff.
So here you don't have the neutron fluid. Here they drip out of the nucleus, so you have these nuclei. So you have this crystal in and free neutrons, and then here you don't have the crystal anymore.
Homogeneous. Like that.
Okay, now it's homogeneous fluid.
Yeah, and then here at this point you go to higher densities, and you might have other species.
What is the source of energy? Compressor?
So for most pulsars that we observe, these are rotationally powered. There are some strongly magnetized neutron stars with fields of up to 10 to the 14, 10 to the 15 Gauss, and then we think the magnetic field is the source of the observed activity. But for most of the ones I'm going to be talking about, these are the rotation powered pulsars. So that's an interesting question that we'd like to know the answer to. So the idea in general is that this is a fossil magnetic field. So you had your field in your star, then it collapsed, and you ended up with a strong field. In practice, this is not quite enough. You can't really explain these strong fields that you observe in these magnetars I was saying, 10 to the 15 Gauss. Then there are various options. So dynamos have obviously been suggested, but possibilities, intrinsic magnetization, various things that could happen. So it's not, I guess the short answer is we don't quite know. It's assumed to be fossil, but it's clear also that that's not enough to explain all of it. Okay, so what we observe, so neutron stars are observed throughout the electromagnetic spectrum. I'll be discussing mainly radio pulsars, so this is how neutron stars were discovered. So what you think you have here is you have a star that's rotating around this axis and magnetic field is misaligned. So if you're accelerating particles here at the poles, you're emitting radio waves, and then as it goes round, you basically have a lighthouse, and when it crosses us, we detect a blip, and then we can time this pulsar. But of course, we observe them also in X-rays, gamma rays, optical, and as of very recently, gravitational waves. So you may have heard that we observed a neutron star merger in gravitational waves. This was this signal GW170817, which has already started to at least give some indications of how you may constrain the equation of state of dense matter, and I'll discuss a little bit later how superfluidity can have an impact on gravitational wave signals as well. Okay, so if we want to look at the superfluid, this point is kind of different because we can't build our experiment to test exactly what we want, but we just have to hope that we get lucky and observe something like this. This was the first glitch observed in the Vela pulsar in 1969. So what's happening is here, this is the period of the pulsar versus time. So the period is increasing, which is what you would expect because you have a magnetic field, so you're emitting electromagnetic waves. So if you just take dipole radiation, you extract energy from the rotation, you spin down, but then suddenly here there was this jump that's instantaneous to the accuracy of the data. Can do a bit better now, but it's still not resolved. The best upper limits for the Vela pulse are around 40 seconds for this event to occur. So there's this sudden jump, and then you start to spin down. Okay, so how this was interpreted? Well, interpreted in terms of, let's see, superfluid. So the idea is that you have some superfluid component in the interior that's storing angular momentum that's decoupled from the spin down of the normal component. And then when you have the sudden recoupling, you have this exchange of angular momentum and you get the glitch. So we model this in terms of, say, multi-fluid, but you could start with two fluids where you have your superfluid neutrons, and then the normal component, you could have more because you could have superfluid hyperons, you could have in the core high densities, deconfined quarks. So there could be other species. But essentially, you write down, let's say, the HBVK equations. But there is a difference here with, for example, the helium case that was discussed, which is that we're not dealing with the condensate and its excitations now, but these are two massive fluids at zero temperature. So you have this X as the component, you have the neutrons and the protons. So these are two fluids, and where do you see that one of them is going to be superfluid? Well, here you have the entrainment. So when I write down the momentum, it's not just mv, but there's a component along the difference, the relative velocity between the two. This is the entrainment coefficient. And then see over here on the right-hand side of the other equations, you can have standard dissipative terms, of course, more than in the Navier-Stokes equation, because now you can have various more degrees of freedom of ways that things can shear against each other, etc. And then we have the mutual friction force. So this was discussed yesterday, later also with Professor Meinen. So this is where we see that we actually have vortices in the system. So this is the standard case for laminar flow. And so the idea that proposed early on by Anderson and Ito was that you have your superfluid neutrons, so you have this component that's rotating and rotates by forming a nice array of quantized vortices. But in the crust, these vortices can actually pin to the lattice. And then you get something like static friction, that's the pinning force completely can balance the Magnus force that you have because you're building up flow between the condensate and the vortices. And so you start storing angular momentum because the crust is spinning down due to the emission of electromagnetic waves. The Magnus force increases. At some point, it overwhelms the pinning force, and you end up in the free regime. So now you have a standard drag force between the vortices and the crust. And so you take it to be linear. This is laminar flow. And so this gives you the standard mutual friction, and it recouples a component, give you the glitch. And so what do we usually take for this, the origin of mutual friction in neutron stars? So in the core, the idea is that what's happening is that you have electrons scattering off the magnetized cores of these vortices because you have entrainment now. So you get a proton current around the vortex, and then electrons scatter, and they give you this kind of value for this dimension as a parameter, which means that for a standard neutron star like the Vela, you would have a coupling timescale of, say, a few seconds, which is more than consistent with what we observe. The question, of course, is what happens in the crust if you have vortices moving. So you can excite lattice phonons, of course, but this effect is thought to be weak. But you can also excite Kelvin waves and the vortices themselves when they move past the pinning sites. I'll come back to that. So, of course, if the vortices are pinned, then you can't spin down the superfluid, and this is how you store angular momentum, but I don't think I need to explain this to you. So I just wanted to give you a feel for the kind of models that we make. So some of the things, there's a lot of things that have to go into it regarding the neutron star, and there's obviously a lot of things that are rather naive regarding the superfluid. So basically, what do? You assume that you are at 0 temperature and that you're well below the critical temperature everywhere in the star, so you just have superfluid throughout, and you take nice straight vortices that go straight through the crust and the core like this. So this is what Carlo was mentioning yesterday. You kind of have to believe that you have an object that's a few Fermi wide, 10 kilometers long, and stays and is tense enough to be exactly rigid. So, okay, let's assume that's okay. And then,
But excuse me, in quantum gases where we have a finite system, the vortices align normally to the edge. And so here,
so the point here is that,
this direction, but not in the other one.
okay, but the thing here is that there's two things. One is that, of course, this system is rotating quite rapidly, so you have this thing, and so the strong pinning region is this shaded one. I'm not sure if you can see it very well. So the point is that it's not pinning only at the edges, you have pinning sites throughout, right? So here, I guess, this is out of scale. In reality, the crust is quite thin. So these vortices that are in here, you could see them as pinned by the edges, maybe. So then, yeah, it wouldn't be exactly straight like I've drawn it. You would expect it to align. But these ones, so this is the strong pinning region, thread through this region. And so just geometrically, these guys are pinned up here, so it's going to be weaker, but these ones are pinned throughout. So I think this is where the strong pinning in, and then you can have a two-fluid model where you take a rigidly rotating crust with protons in the interior as well, because you have a magnetic field, so you expect that it will couple them quite effectively. And then we take mutual friction coupling, and what you can do at this point, if you have straight and rigid vortexes, even though the pinning forces and mutual friction forces are density dependent, you can average them over the vortex, and build essentially a two-dimensional model. And then you would get something like this. So you have a superfluid that's pinned, but this is a rotation rate, it's doing nothing. The crust, so let's say the normal fluid is spinning down, and then at some point you break the pinning, you recouple due to mutual friction, and then they spin down together. So this is kind of simplified, but we can actually build slightly more refined models, and you can try and fit them to glitches in the Vela pulsar. So this kind of works, but the reality is that astrophysics is messy. And if you look at different kinds of glitches in different pulsars, they actually all look very different. So, you know, in the Vela pulsar, you do see something like this. You have this jump, and then you have an exponential relaxation after the glitch back towards the previous spin down rate, which can be explained quite nicely with these models. But some pulsars have just jumps in frequency. Some have an increase in the spin down rate, but no exponential relaxation after. The crab pulsar, which is one of the most observed ones, is even more unique. It, in some glitches, has this sudden jump, but then it also has a delayed spin up, and then it recovers a bit. So there's a lot of phenomenology to understand and explain. So if you want to do something more refined, you do need to try and work your way through these different scales with different tools. So there's a slide that was made by Gabriel Blazowski. So we started talking with Gabriel and Piotr about how to do this, so you know, how to extract interactions between the vortex and the pinning sites on the microscopic scale. And then the thing is that we have a lattice, so we would like, you started developing Marc Antonelli, who's here as well, vortex filament model, so that, and Konrad Buchetti. So this is actually his simulation, I think, where you look at vortex motion through this lattice, and you know, you want to have some average description so that when you average out, you can have a mutual friction that you can use in your hydrodynamics.
Is there any laboratory experiment, I don't know, with helium and maybe porous material or whatever, any experimental system, or you could study something similar to that?
So I guess that's the question I'd like to ask you, because so there are some problems which I'll explain. There were some experiments, I don't know when they were, with Sakadze and Sakadze, they were spinning down spherical containers. I think these were looked at by the group in Melbourne by Andrew Melatos and Van Eyston and explained. There are, I'll show you later, some of the difficulties associated here are, of course, the size of the system, but also the fact that you have vortices in the neutron star that are separated by many pinning sites. So you want to set up something. I guess there probably are things that, you know, people have ideas that I'd certainly like to hear what can be done. So I'm trying to learn what can be done, but of course, to suggest. So, right, so I'm saying here, because it's important, I think this was mentioned yesterday, they'll say that when we do hydrodynamics, we've averaged over all these vortices. So, you know, when we look at these vortex velocities, that they really are averaged over many of them. And we're really not dealing. Yes?
I understand that the magnetic field is not actually aligned with the rotation.
No.
So the protons and the neutrons they make vortices with an angle.
Yes.
So is this angle thought to be the same throughout the interior, or essentially there is alignment in the interior, then it comes out?
So that's an interesting point. I'll show something a little bit later, some simulations that they did in Melbourne. So the point is that you don't exactly know what the field configuration is in the interior. So what we do is you look at the exterior and you can extract, let's say, the dipolar component quite far from the star, which is going to dominate the spin down. Maybe more complicated, you might also have toroidal components in the interior. And so, yes, the large scale magnetic field will have a direction in the interior which will depend on where you are. So you would expect that on average, if you look at your flux tubes, let's say the average vorticity the circulation should align with the magnetic field, and this angle will change because it's not just a constant ray, so it could be potentially quite complicated. So of course it could be tangled. I guess overall it should, once you average, the average should align with the global magnetic field. If it's a dipole, you can work out what it will be in various regions. If it's more complicated than that, if you have toroidal components as well, then you'll have something much more complicated. Okay. So if we start from the smaller scales, so these are some simulations that we did in Melbourne, so they were developed by Andrew Malatos's group together with based on the code by Tapio Timon. So what's being done here is you take the Gross-Vitayevsky equation and you couple it to a spinning down trap. So you have all these spinning sites, and what's being plotted here, so here you have your vortices, and you see as the trap spins down, they sort of knock each other out. They like to move in hertz, so one goes and kicks the other ones, and then this is the rotation rate. You see that when there's one of these avalanches, you get a jump in rotation rate. So that looks kind of nice. You can do some statistics with this as well, and as you would expect, you get power laws for the sizes of these and exponentials for the waiting times. Now this is consistent with most pulsars. You can't say very much because in reality there's not as few hundred glitches observed, but if you go to an individual pulsars, the better observed ones, you get lucky, you have maybe 30 or so. But for some of them you have maybe 5, so there's no way you can do proper statistics and extract the power law ranges from there. Of course, get more observations, we can try to do it better. And also there are a few, like the Vela pulsar and another I'll show you later, that appear to glitch quasi-periodically. So rather than a power law, the sizes seem to have an average size that seem to indicate there's more of a build-up and then event, while many others do look more like this kind of self-organized critical system. Of course, there's many problems here. First of all, obviously, it's a strongly interacting fermions, shouldn't be using GP in the first place, but also here you have, I think there's roughly 100 vortices here. In a glitch, I think there's something like 10 to the 13 vortices involved, so that's a large extrapolation. This would be a rather small neutron star. But the main problem is that here, maybe you can't quite make it out, but you see the pinning sites, the vortices are separated by, let's say order of 5 pinning sites. So it's not so surprising, you're kind of in this situation. It's not so surprising that one of them can start an avalanche and not come out. Yeah, of course. No, yeah. So here, this is I guess you would want to use a tool like this eventually. At least what I would think of doing is to describe a fluid element in the star rather than the whole star, because the numbers, it's just prohibitive.
2D or 3D?
So this is this kind of 2.5D, so it's a sort of pancake. So it's essentially 2D.
Wouldn't it be more appropriate to basically use the
Sorry, I didn't hear.
Pauli equation? Is it better to use the Pauli equation?
You could, but so I think that this is not the main point here. So I think really the issues do relate with scaling it up, and the magnetic field is important, mentioned before, but it is important in the core where you expect to have the flux tubes. When you look at the crust, then protons are mostly in these clusters, so they're not superconducting. And the magnetic field will play a role in, let's say, the large-scale hydrostatic equilibrium, give you the shape of the crust, but not so much in these interactions. It's much more the pinning between the neutron vortices and these ions in the crust. And the other main issue I was saying is that in a neutron star, you are more in this situation. So you have a vortex over here, and then you have 4 to 10 to the 10 pinning sites, and then you have another vortex over there. So you might wonder whether this guy can ever get to that one without repinning somewhere here first. And so you would have some gradual creep rather than an avalanche. So because it's computationally not feasible to scale the simulations up to this limit, you can look at it with sort of 2D methods, And also analytically, we tried to look at this in terms of a scattering problem and to see when the mean free path was equal to the intervortex separation. And it turns out that in general, what matters is how close you are to the critical threshold for unpinning. Because when you get very close, you essentially do get a self-organized system. So the vortices have this pinning potential, but as the Magnus force increases, it kind of renormalizes it. And so then they can hop past many pinning sites and possibly knock on, accumulate, and then when they get close, they can knock each other on. We tried to include this in something missing here. I thought there was something here, never mind. So we tried to deal with this effect of vortices accumulating. So Vadim Khomenko, a graduate student of mine who will be here later on, we tried to describe the evolution for the lag between the two fluids in terms also of another parameter, so the fraction of free vortices. The idea being, if all vortices are pinned, then you shouldn't have mutual friction. Their velocity is exactly the same as that of a normal fluid. But then if you have vortex accumulation, you can have unpinning. And you see that if you allow for this, you develop differential rotation as well. And you end up with waves, instead of just an exponential coupling, you have waves that can propagate in the system. You see you have nonlinear terms here, and you advect this vortex over density. And this is kind of interesting because it allows you to get delayed rise as this propagates out, which you can then fit to these delayed rises of the crab pulsar. And this seems to, you can play this game and try to constrain the mutual friction parameters in the star. And the indication when you do this, and so other kinds of calculations, when you try and look at the activity of the Vela pulsar, so how much spin down has been reversed over time by glitches, you see that this is actually more consistent with the core also playing a role in some of these pulsars. So then you really do need to understand this coupling with the flux tubes. Okay, so this is kind of the idea of the models that we develop, but of course, for now, every time I've put in mutual friction, I've just assumed straight vortices and laminar flow. But it was suggested already in 1970 by Greenstein that you probably have turbulence in neutron star. So the idea here was that, okay, you have vortices that are pinned in the crust, so essentially they're pinned just at the edges, you were saying. And so, but then you have this difference in rotation rate between the superfluid and the normal fluid. So the superfluid stretches, and they want to flow with the superfluid here, so they get stretched and wrapped around many times. So then you can have connections, you start forming loops, and then you end up with a cascade and develop turbulence this way. In fact, if we look, so if we want to write down the evolution equation for the vorticity, in terms of, it looks something like this. So you have a dissipative mutual friction term over here that tends to kill off your turbulence, but then you have the inertial terms that drive it. And if we look at the ratio for typical neutron star parameters, B is expected to be small, B prime even smaller. So you end up with a ratio that's much less than 1. And so in general, you expect turbulence. And on more general grounds, these vortices do have a finite rigidity, so they can bend, they will not be straight. And also the forces acting on them, you have these vortices, so you have cylindrical symmetry. Most of the forces are density dependent and have spherical symmetry. And so they are not the same throughout the vortex, so the pinning force will vary, the mutual friction will vary and try to shear the vortex. And this is the vortex line simulation we did. So also here you have a pinning site and the vortex moves past. If it can pin, it starts to bend. Eventually it will snap. But you see that now at this point, if the superfluid is going around this way, there's always some region of the vortex where you have some counterflow. And then if you try to move on from the sort of cylindrical models that I showed you and do something 3D. So this is a simulation we did in Melbourne for George Howard. So here this is spherical Taylor-Corrette flow. where you have, would be the outer region of the crust where the neutrons are all in the nuclei, and this is the interior where they would be strongly coupled by mutual friction. And then in the crust, of course, you start forming these Taylor vortices. And these are not the same. There is mutual friction coupling, but you can have rapid changes here, and the flow is not the same in the normal superfluid. So you always expect, and then of course, the high Reynolds number, this will go turbulent in classical sense. So you always expect some form of counterflow along the vortex axis. So you would expect standard Donnelly-Glaberson instability. And in addition, even if you don't have counterflow, there are several two-stream instabilities that can act on this. Vadim will talk a bit about this later on in the program, but even if you have standard vortex aligned with the rotation rate and flow around it, there's still many modes that can go unstable. Stability timescales even milliseconds, so quite rapidly. And so you would, in general, expect to develop a tangle. And of course, here I think what we also like to understand and was addressed yesterday is in what order these things happen. So if you develop classical turbulence first and then end up with vortex tangle, or does this happen first? So this is something I'd like to understand from you. And so you expect this transition, and this is possibly relevant for triggering glitches as well. So you may expect that you start to build up this lag between the superfluid and the normal component. So you start off with a straight vortex array, but then at some point you transition to this, so you have an exchange of angular momentum, and the coupling timescales also become very different. So this has been suggested by various authors. I think Andrew will discuss it in more detail in his recorded talk, if you have a look. And of course, the mutual friction is also going to change. So we have this general expression that's suggested by Professor Beinan. And I think what happens to the vortex length was discussed in detail yesterday. And while it's not, you can't quite tell exactly what the dependence of these terms should be, so I purposely left it out. In general, you have to realize that here, of course, we have rotation, so this is going to be polarized turbulence. So you can have essentially two equilibrium solutions here. One is just straight vortices, and then the vorticity will depend just on the rotation rate of the star. And then you can also start lengthening the vortex, and you would expect to still have a term that on average will return the correct rotation rate of the star with which you have to align to. And then vortex will lengthen in terms that depend on the lag squared. So then when you go and put it back into here, you would end up with the standard dependence on the lag cubed, the Gortner-Melling kind of mutual friction. Of course, this makes a difference, because if we take sort of standard laminar form, so we take this linear drag, we go and solve our equations, you end up with an exponential, so you have a nice coupling timescale that you can work with. And in the crust, if you just consider phonons, the lattice, this will be very weak. But then when you change the form, you stop having an exponential, you end up with a parallel. So it's qualitatively different now. And of course, you can just in general look at drag force. So for high Reynolds number, we know that in general, drop something in the atmosphere, you know that the dependence is squared here. So this alpha would be 1, be 2 for Gortner-Melling kind of mutual friction. Question is, what do we do if we want to understand mutual friction due to vortex line moving past these pinning sites? So you would excite Kelvin waves. You now have a length scale that's set by the interaction length for the pinning. There have been calculations of this for high velocities that give you alpha to -3 halves. Of course, for low velocities, this doesn't work anymore, because what happens is that the length scale you look at that's defined by your kappa of the Kelvin waves becomes long enough that you've reached the next vortex, and so you're not adding things incoherently anymore. And what you would expect is to break down because, of course, otherwise it would diverge for small velocities. But even for large velocities, the qualitative behavior is rather different. So there's some plots that Vadim made for me that this blue line is the exponential with the same starting point, so same mutual friction at the beginning parameter, but different dependence. And you see that if you take, so after 2, this would be Gortner-Melling, see it's much slower. But then if you have a rise defined initially by the Kelvin mutual friction, it's much faster than standard exponential. And this could be an explanation for why we see different kinds of relaxations after different glitches, even in the same pulsar, because if the response in some cases is laminar, in some cases is turbulent, then you have a rather different relaxation, evolution of the frequency. And this could also be at the heart of something that's called timing noise. So essentially for pulsar observers, timing noise is everything that's not in their standard spin-down model and is not impulsive like a glitch. So basically any longer timescale fluctuations are generically called timing noise. The spectrum is generally red, varies from pulsar to pulsar, it's also not easy to determine, and I think if you look at Andrew's talk, he will discuss this in more detail and how you could try and what observational tests you could try to do.
What do you mean the spectrum is red?
Yes. So you have a kappa that's quite large.
The timing noise, so
The timing noise, yes.
yes, but red compared to what?
So it's just the values of the kappa that you get, just the values if you take the spectrum and then try and see how it falls off.
Okay,
It's
so this
quite
is
a high value.
the noise spectral density that has a
Yes, so this is, and then it has a decreasing, and then it varies from pulsar to pulsar, and so it's not so straightforward to determine. Okay, and then you're getting low on time. So, of course, there's this issue of the vortex flux tube interactions, because now, the vortices are magnetized. We said the neutron vortices because of entrainment, and we expect to have a type 2 superconductor, so to have magnetic field confining flux tubes, and then there's an energy penalty for these neutron and proton vortices to cut through each other. So on the one side, you expect thinning, and then of course you also expect dissipation. And the setup will depend strongly on the inclination angle. So these are some simulations that Lisa Drummond did with Andrew Malatos. And see and also the arrays that have different tensions, etc. And you see that you end up with some tangle once you start inclining them one to another. And this inclination angle that Carlo mentioned is actually very important in determining, for example, here the number of pinned vortices that you have in the system. And as I said, there is some indication that probably you need to involve part of the moment of inertia in the core in large glitches in the Vela pulsar. So this kind of thing is very relevant. So just to move on very quickly, say the last thing, I mentioned gravitational waves. So why does this kind of topic matter? Well, it matters not so much, I'm not going to focus on these in-spirals that you might have heard of, but it matters for continuous gravitational waves. So basically, a gravitational wave pulsar, something that's on all the time. And there's various ways you could do this. What I'm interested in is that you could have oscillations of the neutron star that couple to the gravitational field and give you an observable signal. So you could do gravitational wave astroseismology as you do with instruments like Kepler for main sequence stars, or as we do for the sun. And in particular, one of the modes that's interesting is the so-called R mode. So this is a toroidal mode of oscillation for which the restoring force is a Coriolis force. So it's the analog of Rossby waves in the ocean. And it's interesting because it can be driven unstable by gravitational wave emission. If gravitational wave emission can remove angular momentum, it allows the mechanism to transition to a state with lower energy and angular momentum where this mode is growing. And the mode can grow as long as viscosity doesn't damp it faster than gravitational waves drive it, of course. So we're interested in understanding where this is possible, because if you have something that grows to large amplitudes, of course, you can try and detect it. And for a standard neutron star model, so neutrons, protons, electrons, no exotic particles in the core, no dynamically significant superfluid degrees of freedom or magnetic fields like this, you have an instability window that looks like this. So this is the rotation, it's normalized. There's the rotation rate of the star. This is core temperature. And in these dark regions, the mode is damped either by bulk or shear viscosity. But you have a whole region over here where the mode could be unstable. And then we can go and look at various systems, because what you would expect is that, you know, when the mode grows, so we can look at systems that are old. Let's go here, where at old accreting systems in which we can measure the spin frequency of the star and the temperature, and we can try and populate this diagram. It turns out that you see that there's a lot of them sitting here. And we don't really expect to see them sitting here, because if they are emitting gravitational waves, they should spin down quite rapidly and exit the instability window, if the mode can grow to large amplitudes. If it were to saturate at lower amplitudes, then you would see them on all the time, which would be good, but they should be close to this region. They should never be sitting in here. And so, you know, why are they there? Clearly, the physics that we put in this instability window is not quite enough. So we have to understand what's happening here. And actually, strong mutual friction can fix this for you in some way. So if we assume that you have vortex flux tube cutting, then you get these curves here. So these systems would be stable. So these are two models where we've assumed two different forms for the pairing gap in the interior. And then to do this, and in fact, the pinning between vortices and flux tubes can be strong enough to saturate the R mode. Okay, so run out of time, I think, and yeah, finished.
You said that those points may quite rapidly goes out. What does it mean, quite rapidly?
So quite rapidly means,
million years.
no. So what?
In which scale?
No. So in this scale, it means that if the R mode were large enough to get a system into here, so it heats up because of the shear from the unstable mode, and then it spins down, it would spend maybe a couple of months here, but then it has to cool and spin up because of accretion, which is like 1,000,000 years. So the duty cycle will be really short. 2 months here, 1,000,000 years here.
But 2 months is much smaller than the age of neutron star, and therefore you don't have to have these points inside at all.
Yes.
They all goes out.
You wouldn't want them, they shouldn't be here, but then when you observe, there's a lot of them there. So it means that this window that I've drawn doesn't work, right? Because I shouldn't find all these systems sitting there. They should have all spun down. We'd have to get incredibly lucky to catch one, and it should be spinning down fast. So the point is, I need to change the window and add either additional viscosity or a mechanism to saturate the R mode at such a low amplitude that, sure, there is an unstable R mode, it's emitting gravitational waves, but it's so weak that it's doing nothing to the thermal or spin evolution of the star. So the point is that, you know, the plain vanilla neutron star model isn't enough for this instability window. And so you need to add something else. I'm saying one of the things can work is that if you have strong interactions between neutron vortices and proton flux tubes. Because yes, you're right. It's very short time scale here, so you should never catch them there. But the thing is that you do. Okay, and so that's it. This doesn't, I'll skip this. And so these are my conclusions. I just wanted to give you a flavor for what superfluids and neutron stars, what kind of problems we have of pulsar glitches and how they can guide our understanding and what we want to understand. And of course, the limitations of these models. And then there's many open questions. I've just listed a few here. So, you know, how we describe neutral frictions when we have Kelvin waves, especially because of low velocities. So what you do close to this unpinning threshold. Also, what happens at the interface between S and P wave pairing, you get some kind of instabilities as you do between different phases of laboratory superfluids. How does turbulence develop in the presence of pinning? Because here as well you have these pinning sites, so you're sort of dragging a normal fluid, you sort of have a grid of pinning sites that you're dragging through your condensate, so something to understand, and obviously understand the timescales and how they relate to glitch observations and understand what's happening in the core. Okay, thank you.
All right, time for some additional questions.
You mentioned about noise over gravitational waves. One can generally speaking estimate the level of that noise by just taking a model, neutron star, and estimating the number of total new stars in the observable universe. Now, and this level of gravitational waves is many decades below the current sensitivity of sensors, or more or less above.
So I'm not sure I understood. So do you mean like some stochastic signal from just having this? So you
what was observed up to now, just a few events.
Right. So
huge.
Yes. So
On just a little bit above the sensitivity level.
Okay. So I think there's maybe two questions there. So in terms of these actually detecting individual signals, the kind I showed you, these armors, obviously this depends a bit on the model, how strong you think they will be, but for general models, we are starting searches for these things, and you know, we are at the kind of sensitivity where if you're on the lucky end, you will get it. If you're on the unlucky end of your parameter space, you might have to work a bit more, but it's roughly right. So the kind of stochastic signals that you're mentioning, then this is a bit harder.
Well below the...
Yeah. So this you could try and build up if you have, because one of the ideas is that these armors are actually what's spinning down young neutron stars. So you have a neutron star that starts hot and rapidly rotating. It enters this instability window from the other side, the hot side, and then the armor spins it down to the spin periods that we observe in the current pulsar population of, say, tens of Hertz. So if you have that mechanism is actually what's doing it, then you would have many systems that you have to sort of estimate how many supernova you think you have, and how large you think the amplitude of the mode will be. And then you can work it out. So there are claims that this could be detectable in the near future. I don't think we're quite there yet, but this is in fact a promising thought. This is in fact a mechanism that people do.
Question in the...
Yeah, so this is a little bit confused about the nature of the pinning that you've been talking about, where you're pinning on the crust and then also pinning on the interior. Is there some speculation or of the nature of what's producing the pinning?
Right. So in the crust, you have these clusters. So the assumption is that it's energetically favorable for the vortex to have this very high density blob of material inside rather than outside. And so you have pinning in some regions. It's the opposite. It's energetically favorable to have it outside. And in fact, this is what comes out of Gabriel and Piotr's simulations and Norel, where you have repulsive pinning. But there it's essentially the difference that you get in, say roughly, it's just the difference in condensation energy of having a normal interior and taking a nucleus which is much denser than its surrounding gas and sticking it inside or outside.
So it's not pinning very deep then?
So there in the crust it's that. For the flux tubes, there it's different because there it is actually mostly the overlap of these magnetic fields, and it is I mean, you would also have an energy penalty from the condensation energy, but it is mainly trying to cut through these magnetic fields.
Okay, about vortices. I understand that you consider just ordinary vortices, single quantized, as here in 4, right? So is it possible to think also about, say, multiply quantized vortices, like in real 3D you have only quantized vortices, or even giant vortices which you can observe in superconducting sometimes?
So the question is it possible to think about multi-quantized vortices or giant vortices?
I think we'll have developed models where they were looking at vortex bundles moving through. And then I think you can have some of these stranger structures in the core of the neutron star where you go to different cores. You can have color superconductivity and various kinds of things. I think Andy probably knows more about this than I do. So people have thought about these. I'm not so much of an expert.
A question, I think this was asked earlier. How do we interface all of this theory with experiments that can be done to start understanding the basic mechanisms? Because clearly, the neutron star is a complex beast, and there's a lot of stuff going on there. So how do we validate this stuff? It looks like there are two paradigms. One in which the nuclei play an important role in pinning the vortices and being important for the mechanism of glitch. And then the second paradigm is one in which you have a vortex tangle that could by itself produce this metastability. The general question to the audience, including you, is are there experiments that went into to look at the distinguishing features between glitch-like behavior in these two systems?
So are there experiments that can be done to look at the distinguishing features between glitch-like paradigms?
Yeah, the pinning paradigm and
the pinning paradigm, and then complex network tangles.
Yeah, and I guess these two need not be separate because you can have both things happening. I mean, perfectly true that you can, if you want to get power law statistics for the sizes, you can do this with just turbulence and you don't need to do the pinning. Then you might wonder, though, how do I get the more regular kind of behavior? So you might have the pinning happening, but then in some cases, for larger glitches, some regions of the star, you end up with a turbulent response. So you actually see a different kind of frequency evolution after the glitch, possibly, although the glitch itself was given by pinning. So I think it's more
complicated. You're suggesting that we already have evidence that just one pinning-driven mechanism is not adequate to explain the diversity that we are seeing in astrophysics.
So I think, well, maybe evidence is not strong, but for example, if you look at the Vela and you try and estimate how much spin damage reversed by glitches, and then you try and put in Nicolas' calculations for entrainment in the crust, which is quite strong, you see that you can't do this with the crust alone, and so you would like to involve part of the core. Then there's other models that also work with this, so that maybe hints. Evidence is maybe too strong in this case, but thing is that you have the observations you have, so it's hard to do it from that point. So of course, if you can do something with experiments that you actually have control over, that would be better. Of course, one way is if you develop these simulations for the interaction between a vortex and the pinning site. So you want to get the pinning force, and you use the time domain functional theory methods, then these ones can actually be validated against experiments, so you can use that as a stepping stone. But of course, the question to everybody here is, apart from doing this from a theoretical point of view, I don't know if there are actual experiments that one can design that would provide an insight to some of these questions. So that's a question for everybody else in the audience.
One final question. We will have a discussion session about this on Thursday. Hopefully Andrew can join as well.
So I invite you all to, we'll put the slides online on Andrew's recorded talk, so please do go.
So there will be an opportunity to ask and have more thorough discussion.
So I have a general question. In the merging of these two neutron stars that was observed, I remember people saying that you had access actually to the deformation of the surface modes, in the final state of the version. Can you say something about what kind of quantity can you get on viscosity, on this is fully relativistic at this time, so I'm just
Yes.
wondering.
And it's also pretty hot, so it's not
Yeah.
so.
Up to which rotation speed can you, I mean, this happens, what you described today.
Well, I mean, there it's a completely different system, right? Because you start to probe you have the imprint of this tidal deformability very close to merger. So at that point, the two stars are touching. The temperature is going to be much higher than the superfluid transition temperature, probably melted.
So you
for us.
cross, I mean,
So I think
in this process, you
at this
go
point,
with this,
I would say that what I talked about today is not really applicable to the last few orbits for merger. And then what you try to probe there is actually the tidal deformability, so the imprint of the equation of state with the interactions between the neutrons.
All right.
Can I have a comment, not a question?
Okay.
Just a comment, because he asked whether there is something that can help you with the gravitational normal turbulence happens first. First, 10 years ago, we published a paper. We answered this question because this JFM paper we have propagation of superfluid vorticity within the normal turbulence. And there we calculated all the scalings regarding the time. So you could actually do this.
Okay.
It's 2008.
All right. Thank you very much. Again, we'll have a session on Thursday. So coffee break now. We come back in at 10:30.